and we will try to find the general features of nuclear reaction cross section when the projectile is either an uncharged particle like your neutron, or it is a charged particle like proton. Okay, so this is what we will discuss now. Fine, so let us start. Now the first case is that of uncharged particle. Okay, so uncharged particle, basically neutron. So a neutron undergoes a grazing collision just touching scenario, grazing collision with nucleus. Let me draw the picture for you. So this is basically the schematic diagram, as you can see, and this small b is the impact parameter, right? And so this is the radius r of the projectile. So let me write down the cross section. So let me write it in a separate page. So the cross section I can write as approximately pi r plus r prime whole square, where I have considered, you see, the impact parameter b to be the sum of radii of projectile as well as this is the projectile. Okay, this is my projectile and this is the target. The projectile's radius is say r prime, the target's radius is say r. So b is equal to r prime plus r, something like this. So this is the cross section I have written. Now let me write it completely. So this is equal to pi r0 square into projectile, mass of projectile plus mass. Okay, I have used the atomic mass. So basically I have used the relation between radius and the atomic number. Now, okay, if we apply the classical mechanics, so basically we will be considering semi-classical approach. You will see why I will call this semi-classical. So first let me
mass गुलो
हाँ बोलो. Yes, good. Do point it out. I can sometimes miss points, right? This is 1 by 3. Yes. Okay. So using, now let me use the classical mechanics. So let me write down the orbital angular momentum. So we have L is equal to R cross P, and this is just your P into B. Now in the case, if we use quantum mechanics, then what do we have? L is replaced by LH cross, and so in this case we can write P as H cross by lambda cross. We can write like this. See if there is anything wrong with this expression. Nothing. So basically we can write LH cross is equal to H cross B by lambda cross and this gives us B is equal to L into lambda cross. Now you will be wondering what is happening, but this expression is not quite right, because L is quantized, however B is not, right? In quantum mechanics we talk about the quantization of L, however B is not quantized. Now how do we get around this? How do we correct this? So sometimes we get around this fact by associating B. Let me write it. L is quantized but B is not. Problem. As a result we have a problem. This problem is overcome by associating B with certain energies. Sorry, not energy, it will be basically ring, but again it will correspond to different energies or zones on the target. Let me show it to you. This is basically a schematic bullseye view of the target nucleus. So what is happening? Basically, if your projectile is coming with certain impact parameter, since the angular momentum is quantized, I am now using this concept to make zones or different rings for the projectiles, right? Basically I am using these zones for the impact parameter. Now, so this figure in a way it suggests that for head-on collision what will happen? What is head-on collision? Bolo? Head-on collision is when this happens. That is head-on collision means L equal to 0. Now in this case the head-on collisions means of course L equal to 0. So in this case the B will be between 0 and lambda, right? Whereas for L equal to 1 collision, so this is the first case, head-on collision. Next we have the L equal to 1 collision. What happens in this case? In this case the B is between twice lambda and lambda. Students, are you understanding this? You see I am using the different zones. So this is the L equal to 0 head-on zone, and this is L equal to 1 zone, this one. So basically what we observe is that the cross section is larger for larger impact parameters, and these larger impact parameters are associated with larger angular momentum. Okay, so let me write L plus 1. Okay, so this is just sigma L. What about the total reaction cross section? The total reaction cross section is obtained by summing over all of them. Right. Now when we do this sum, this L will go to a certain maximum, L max, and as a result, after this sum, we will get this result. Okay, now we can write for this maximum angular momentum L max, so L max is equal to the radius r, the largest possible, right, radius r divided by lambda cross. So this means L max plus 1 equal to r plus lambda cross by lambda cross. Any issues? কাউর বুঝতে কোনো রকম অসুবিধা হচ্ছে?
না স্যার।
Very basic ideas these are. So yes, we can write the total cross section as a result of this pi into r plus lambda cross whole square. Now you see, this total cross section is proportional to the size of the target nucleus and the size of the projectile nucleus. However, the wavelength of the projectile, which is lambda, it goes to infinity as the projectile energy, it goes to 0. And so the cross section for neutrons at low energies can be very large. Okay, now here we have used entirely semi-classical approach. Now let us try to use more of quantum mechanics and see how things change. Okay, so you see, in quantum mechanics we can write a similar expression for the total reaction cross section. So this is just pi, again lambda square cross L equal to 0, this time to infinity, see, twice L plus 1 into TL. What is this TL? This is basically your transmission coefficient. And it varies between 0 and 1. Now this transmission coefficient basically expresses the probability that a given angular momentum transfer L will occur. What happens at high projectile energies? At high projectile energies, we have TL equal to 1 for L less than equal to L max. And what about the other case? So this is equal to 0, of course, for L greater than L max. Now this is known as sharp cutoff limit. Fine. Now what happens at lower energies? Just a second. At very low energies, we have this sigma total is proportional to pi lambda cross square into root e, which is again proportional to h cross square by twice m epsilon again into root e. As a result, we get this whole thing proportional to 1 by square root of energy. Now, such behavior of the cross section for neutron induced reactions. Neutron induced reactions. For neutron induced reactions at very low energies, we have this sigma total proportional to 1 by this behavior, and this is known as 1 by nu behavior. Okay, কাউ কিছু বুঝতে অসুবিধা হলে বলো. Any questions? See, in quantum mechanics, when you did the barrier penetration problem, same type of transmission coefficients entered. Now here we are using this while considering the total cross section. The concept is same. This is just one of the possibilities. I am using a very basic model for this TL. See, when L is less than equal to L max, TL is 1, otherwise it is 0, and that's why it is known as a sharp cutoff model. I can use a different type of behavior for TL and see the try to find the total cross section. Okay, that will be a different model. Here I have talked about one of the most basic possibilities known as the sharp cutoff model. Fine. Now, so we have considered when the projectile is neutron. See, this was the bullseye picture. We all considered, so we considered the case of neutron undergoing grazing collision with nucleus. Now next, and this will be the last part for today's class, we will now consider the interaction of charged particle with nucleus, like that of Rutherford scattering. Okay, so here you can see a schematic diagram for a charged particle induced reaction. Fine, this is my charged particle Z1 interacting with the target. Now, as the charged projectile approaches the target nucleus, it feels the long range Coulomb force, and as a result it is deflected. Fine. Now, as a consequence, you see the range of collisions corresponds to smaller range of impact parameters. If the incident projectile, if incident projectile has an energy epsilon at infinite separation from the target nucleus, then at the distance of closest approach, let us call this R, its kinetic energy will be equal to epsilon minus B. What is B? B is basically our Coulomb barrier. So in this case, situation will be different because of this presence of Coulomb barrier. Fine. Now, at the point of closest approach, let me write in the separate page. Okay. At the point of closest approach, the momentum p of the projectile is basically 2mt to the power half. Thus, we can write, you see, this thing as twice mu to the power half into epsilon minus b to the power half. Or we can write P equal to 2 mu epsilon to the power half into 1 minus B by epsilon to the power half, where basically mu is the reduced mass, right, of our system. Now, just a second. Okay, fine. Now, classically, for orbital angular momentum, we have L is equal to R cross P. Okay, so this gives us L max equal to R. We are using the expression of the previous page to the power to 1 minus B by epsilon to the power half. Now, quantum mechanically, what happens? So, this was classically. Now, quantum mechanically, we have L gets replaced by LH cross. So, we can write in this case sigma total is equal to pi cross L max plus 1 whole square. Now, if L max is much greater than 1, then I can just write it as S cross square lambda cross square into L max square, and so we have this result. So we can write this as pi lambda cross square R square into 1 by again lambda cross square 1 minus B by epsilon. Now here these two get cut. So let me write the final expression in the next page. So we have basically sigma total equal to pi r square. See what a simple expression, into just 1 minus the Coulomb barrier effect, right? Remember, this expression is valid for energies greater than the Coulomb barrier. So, any questions? So, here you can see the combined general feature of cross section, this one, for both charged and uncharged particles. This one is the case for the charged particle and this is for the uncharged particle. See, and this value is the geometric cross section pi r square. So behavior of cross section as a function of incident projectile energy.